Okay, we're doing some examples here of double integration in polar coordinates. I'm just going to record individual examples one at a time so that the recording doesn't get too large. But the examples I'm going to do today are part of this module Vector Calculus .213a. This is just double integration polar coordinates and examples of. The first example we want to do here is it's a classic, simple, but illustrative example of a volume integration in polar coordinates. And this is what the problem would say. It would just say this. It would say, find the volume of the solid bounded by the graphs of, and they give you some number of graphs. And by graphs just mean plots, functions, etc. And you have to first kind of figure out and visualize, well, what region is this thing? And once you do that, you have to do that first, really. Then you can kind of discern, well, how do I want to integrate this? And when we first start, it's not obvious we're going to use polar coordinates. In this particular problem, it will become obvious to use polar coordinates, but that's not the start of it all, okay? So here it says, so bounded by graphs, so we have x squared plus y squared equals 4, z equals the square root of 9 minus x squared minus y squared, and z equals 0. And each of these is a kind of a separate kind of object in 3D space. And 3D space is the operative word here. When we're doing double integration, okay, we're talking about solid, we know we're in R3. And when we know we're in 3D space, we know everything, even if it doesn't say Z, we know it's dependent on Z, or at least should be thought of as extending along the Z direction. So what I'm going to do is just define each of these three curves first, then it'll kind of be obvious what their intersection is, and then we'll calculate the integral of that, and it'll be very straightforward. So the first thing is x squared plus y squared equals 4. Okay, so x squared plus y squared equals 4, if we think of this in x, y, z, okay, x squared plus y squared equals 4 is a circle in the xy plane of radius 2. Okay, so it would be like this, right? Okay, radius 2, this is 2, right? That's what it looks like in the xy plane. But because we're in R3, we have to think of this as being true for all z. So this thing is true no matter what z you have. So actually this is a cylinder, a vertical cylinder, okay, that goes to z plus infinity, and then it also goes down to minus infinity. So it's an infinitely long cylinder in the vertical direction, whose cross-section is a circle of radius 2. Okay? So that's the first object we have, vertical cylinder. The second object we have, actually let me do the third one first, z equals 0. So z equals 0 also seems simple, and when you have just a single variable equal a constant, that's a plane, okay? And so z equals 0 is the plane, well, at z equals 0. And I can draw it on top of this surface pretty easily. It's this entire xy plane, but only at z equals 0. So it goes to infinity in y, and infinity in plus minus x, and plus minus y, but it's only at z equals 0. So it's cutting this cylinder in half. Okay, so now I've got a vertical cylinder and a downward cylinder, and I've got this plane cutting it in the middle. So, okay, so that's defining it. Now I just got to figure out, well, what's the third limiting function? Because right now the volume is infinite, no matter how I define it. So we're not ready yet. So let's look at this guy. Z equals the square root of 9 minus x squared plus y squared. So that is a sphere, what's the top part of a sphere of radius 9. Now that's maybe not super easy or obvious to see. If I rewrite that as z squared plus x squared plus y squared equals 9. So I just said z squared equals, I took the square root of the square of this, and moved the x squared and y squared on the right hand side. Then that's probably something you're used to seeing, right? Because the general equation for a sphere in 3 space is this, okay? So this thing is a sphere of radius 3. Now, when you go back, the z for a sphere, the top half of the sphere is plus square root 9 r squared minus x squared minus y squared. The bottom dish of the sphere is negative that. So when we have just z is positive, z is always greater than 0. So that means we're in the upper half plane. And this dish cuts through this guy, okay? Okay, so we have this upside down bowl sitting on top of the XY plane, and then there's a vertical cylinder running through it. So the final surface that we have is really a cylinder, okay, sitting here with a dome on top, okay, and the dome is this z equals square root 9 minus x squared minus y squared, and this circle, right, is radius 2 in x and y, okay, and all we have to do now is find the volume of this thing, okay. Now, it's not, even though it seems easy, it's not easy to just do this by geometry alone, because it's hard to figure out the intersection of the cylinder and the sphere, okay? But that's the region that we have, or the volume that we're trying to figure out. Now, so when we express this as an integral, I'm going to erase this center curve now for a minute. Okay, so that's the thing we're integrating, or the volume of which we have to calculate. So if we want to think of the volume of something as a height over a floor, okay, the floor is going to be in the XY plane, and we have a natural varying height above that. So I want to calculate the volume as the integral, right, of this dome, okay, which is the height over the floor, where the floor is r, and r is this circle of radius 2, okay? So that's what the volume of this thing is going to be. You could, in principle, cut into other pieces, but this is the natural one. We have a simple floor, and we have a height above that floor, which depends on position over the floor, and we're calculating the volume of that thing. So that's why we choose this as what we're integrating over a, which runs over r, which is the floor under this function. Now, when we do this now, this is obviously a natural to do in polar coordinates, because our limits in r is 0 to 2. Our limit in theta is just minus pi to pi, or 0 to 2 pi, because we're going around that whole entire circle. And then the vertical is just this function of x and y. Now, when we're looking at functions in polar, what you want to look for are opportunities, in particular, for things like x squared plus y squared, because those will simplify right down to r squared in terms of polar coordinates, right? So what we have then here is this integral volume is actually an integral over r of 9 minus r squared dA, and I'm going to expand r as 0 to 2 pi in theta, 0 to 2 in r. This is the height, and then r d theta as always. That's dA. This is the function we're integrating. These are the limits over that circle. Okay? And then at this point, it's just a matter of execution. And you can already even see too, it's going to be relatively simple to calculate this thing. So I'm going to write this integral over here. Okay? It doesn't matter whether I go 0 to 2 pi or minus pi to pi, you get the same answer here. Okay. Let me just erase this and we'll just execute. Okay, so I'll do the r integral first, and I'm just going to do the antiderivative here first. Well, I'll do it like I did it in the notes. So we'll just write this whole thing out and do it in one shot. Okay, so I'm going to have r equals 2, r equals 0, because I'm going to make a substitution here. U equals 9 minus r squared, so I'm going to let u equal 9 minus r squared. So du by dr is minus 2r, which makes r dr equal minus 1/2 du. That's a pretty classic substitution that we're going to have. So this whole thing will look like minus 1 over 2 du, okay, square root u du d theta. And when you leave everything in the integral here, that's why I leave r equals 0, r equals 2, because I've converted the inner one to an integral of u. And I'll convert it back once we've got it. Okay, so this thing becomes minus 1/2, and then 2 over 3, and u to the 3 over 2, and that's evaluated at r equals 2 and r equals 0, and then d theta is wrapped around the entire thing. We'll talk about the d theta at the end of the problem because we could be handling it now, but we're not gonna. We're gonna do it slow way. Okay, so this thing becomes minus 1 over 3, 0 to pi, and then I'm going to put the u back in as 9 minus r squared to the 3 over 2, and now we're going back to 0. R is 2 to 0, d theta. Okay, so this is minus 1 over 3, 0 to pi. Okay, and then we go in and put the 2 in, so I have 9 minus 4. Okay, and then minus RB 0, 9 to the 3 over 2. Okay. And so that thing, if I take the negative sign here, 9 to 3 over 2 is 3 squared, 3, 2, so that's 3 cubed, so that's 27. So this becomes 1 over 3. I've taken the negative sign here, I'm going to switch the order. 0 to pi, 27. Right? Here, I'm going to do it now. This is all a constant, so this should all come outside the integral at this point. This becomes 1/3. Then I've got this one, 27, minus 5 to the 3 over 2, which you can't really do a whole lot with. And then we have 0 to pi d theta. Okay? And so this thing here, right, just d theta from 0 to 2 pi, that whole thing is just 2 pi. So this whole integral then becomes 2 pi over 3, because this here is just 2 pi, so that goes there. 27 minus 5 to the 3 over 2. And that's the answer. Okay, it's kind of a goofy answer. That's why it's actually hard to come up with just on its own. But that's the answer for this crazy volume. Okay, quite easy to do, just a few lines, and I could have gone faster in terms of polar coordinates. Okay, now I want to make a point here, way back at this stage right here. So that's the answer to this. That's how we would do it. Let me just kind of go back to the beginning for a second, because there's something that comes up quite a bit. It's a special case, but it's not a rare case. So if we look at this guy, v equals, and I've got this 2 pi, the theta part. I've got an r part. I've got a function here of r, dr, d theta. Okay, this whole thing is only dependent on r. This is a special case. Okay, it's only r. So it's all a constant with respect to theta. The other thing is the limits of integration are not functions of theta. Sometimes they are, but here they're not. So I guess you could think of this a couple ways. We could have changed the order of integration, okay? Or you could say I'm going to take theta right out, but both ways, this integral changes to the product of two integrals. So normally these things are nested, and you can't generally do this. But if the integrand is a function of just one, and the limits are functions of constants, then you can separate them off, right? And so we have the integral from 0 to 2 pi of d theta, and then the integral from 0 to 2 of 9 minus r squared r dr. So this thing is equal to 2 pi times the integral that we actually went ahead and did. Right? And you'll see this actually when we're doing polar integration or higher dimensions. When we can integrate out one variable right off the bat for free, and this d theta could have done that, you'll often see it might be written, and then they'll just right away write 2 pi. Or sometimes it's so obvious, they'll just write 2 pi right off the bat and not even show it as a variable integration. Okay? But that's the thing you can do. So sometimes the double integral becomes the product of two integrals, but it's a special case. Not rare, but special. Okay? Okay, so that's this problem. That's maybe one of the most classic type of polar integration problems, where we're finding an intersection of surfaces or shapes, we naturally have a circular symmetry in the XY direction or on the XY plane, and it sets up perfectly for polar coordinate integration. Okay, we'll do another problem.